Hello all. We'll be starting with the first question in signals and systems. So this is a mix of the Fourier series and some basic signal expansion. So we'll be talking about that as we go through the question. So the question says that the Fourier series representation of an impulse train is denoted by S of t and summation del t minus n t naught n spanning from minus infinity to plus infinity. And we are asked to represent its Fourier series representation. So to begin with, first let's see what is S of t. 0 t S of t. So to S of t is I will plot n for plus minus 1. Let's take some 2 3 values, that will be enough. This is at 0, okay, minus 2 minus 1 plus 1 plus 2, and the signal repeats. Now it is set at t naught. So the first sample will appear at t naught, 2 t naught, minus t naught, minus 2 t naught. So whenever they give such a function, it is better to first expand it for a limited number of n. Say for example some 2 3 values will be sufficient. Now we see that S of t is a periodic function with period of t is equals to t naught. Now we are asked to find the Fourier series representation of this, and by definition we know that Fourier series says any periodic signal can be represented in terms of its complex Fourier coefficients. So let me explain this. Any periodic signal, this is a periodic signal, can be represented in terms of its, so well the actual statement is any periodic signal can be represented in terms of its weighted complex exponentials. Let me just erase this. Complex exponentials. Okay, so this is our, we'll go word by word, weighted complex exponential. So we know that this is a complex exponential and this is the weight or the factor of each exponential. So if we consider our problem, then x of t is nothing but S of t and summation, everything else remains the same. Let's keep it aside for now. And this is the Fourier series coefficient. Okay, now to find Cn we have this formula. Let's write in terms of S of t. S of t, x of t doesn't make any difference. J omega naught nt dt. Now to explain this, or rather this means integration for one period. Now one period might mean 0 to t naught, or t naught to 2 t naught, or maybe minus t naught by 2 to plus t naught by 2. Okay, so Cn will be 1 by t. Now we know that for any continuous signal, it is the information under it is represented in one area. That is to say, now if I want to convey the information of S of t in one period, I will take 0 to t naught, but this doesn't make any sense because at 0 we have an impulse and at t naught we have an impulse. So instead of that, what I will do, I will take t naught by 2 minus t naught by 2 and plus t naught by 2. So I will be taking the integration in this area. So my integral changes to minus t naught by 2 to plus t naught by 2, and s of t is now del of t dt, because we know the definition of del of t. And there is one more important property in this. This is called as the integral property of impulses. That is to say, suppose we have the range t1 to t2, x of t del of t minus t naught dt. Then if we just get into the results, and first there are two conditions. If t1 less than t naught less than t2, that is t naught is lying within this range, then I will be simply x of t at t is equals to t naught. Otherwise I is 0. So if we use this formula, then Cn turns out to be 1 by t naught. Now for time being, let us consider this as some general function x of t. This will be t del of t minus 0. So our integration is now e power minus j omega naught nt at t is equals to 0, which turns out to be 1 by t naught. So if we substitute this in our s of t function, s of t is n equals minus infinity to infinity 1 by t naught e power j omega naught nt. And since omega naught is equals to 2 pi by t naught, and I think this is the most familiar one, e power x, this can be written as exp of x. And one important concept is here e is not equals to 2.718, so one should avoid that confusion. So s of t turns out to be n equals j 2 pi by t naught nt. So this is the Fourier series representation of s of t, and the answer is option D. So thank you.